Hey, welcome back to Math with Patrick. Today's August 2nd, and we're solving problem number 245 from the Daily Epsilon calendar. And like with all the problems from this calendar, the answer should match today's date. And if there aren't really any instructions, we can assume that we're solving for x. So this x right here should match this 2 for September 2nd. So that tells me that the answer to this problem, or rather this infinite sum, is going to be pi over 2. So once we have some kind of conclusion where this guy is equal to pi over 2, we'll be done for today. The way I'm reading this initially is that we have some kind of infinite sum where, like, first off, we plug in n equals 0, evaluate it here, take the arctangent function and stick it on that number, and then we're going to add that to whatever happens when n is now equal to 1. And then we're going to increment n all the way up until this top number, and it happens to be infinity. So this sum keeps on going forever. So just to take a look at what it looks like, we'll do arctangent of, and then plug in whatever happens when n is 0, which looks like it's just 1 over 1. And I'll get into what arctangent means in a sec, but at least for now, I want some kind of visual representation of the infinite sum. So I'll do a few more terms. We're going to get arctangent of, and then whatever happens when n is now equal to 1. Looks like it's 1 over 3. And I'll do like 2 more terms, why not? Looks like when n is 2, we have 4 plus 2 plus 1 in the bottom, so 1/7. And let's just do like one more term after that. Actually, I noticed that this is a quadratic expression, and so it has constant second differences. That means if you find the number to add from one to the next, and then you do that a second time, this second number here is always constant for any quadratic expression. So I know that it's going to be another 2 again, which means that this is a plus 6, which means this number right here is a 13. And I could have directly solved for it just by plugging in 3. It's not that hard, but just something I noticed at least, that we have a quadratic in the bottom. And this pattern keeps on going forever, so I will do a plus ... here at the end just to say that this is an infinite sum. It keeps on going. Okay, let's read this one together. Arctangent of 1 over 1. Actually, I think it might be useful to talk about the tangent function first. This one inputs an angle and then outputs a ratio, where if you think of yourself on a right triangle, and this is your angle right here, this resulting ratio is the ratio of the side lengths, the opposite side length, opposite of the angle here, divided by the side length that is adjacent to the angle. Not this one, because that one's the hypotenuse. So whenever we do tangent of an angle, it's always equal to this opposite side length divided by the adjacent one right here. And the only difference between tangent and arctangent is that arctangent is the inverse function. So it will just flop the input and output of the original tangent function. So we have arctangent of, and then we'd input opposite over adjacent here, and then we'd get back some angle. I'll just put theta to represent that angle. And so all of these arctangent summands here in our big sum kind of look like right triangles to me. Like, for example, this one says draw a right triangle whose opposite side is 1 and the adjacent side is also 1. And then your reference angle can be in this corner right here. This one looks like an opposite side of 1 and then an adjacent side of 3. And then the reference angle is right here. This is also a right angle. And so we could do this for every single one. Let's just draw the last one. And it doesn't have to be whole numbers either. Like, this could be 1 and this could be 1/7 as long as they have the same ratio. But at least I think for now it's easiest for me to think of this with whole numbers. And the arctangent function returns angles as its output. And so it's essentially like we're adding up all of these angles right here, and we're supposed to get pi over 2. This first angle looks like 45 degrees, or pi over 4. But then I don't really know how to eyeball these next 2 angles. I mean, I can eyeball them. I can say that this is like roughly 30 degrees, I guess. But I know it's not exactly 30 degrees. This is like maybe like 15 to 20 degrees, but I know it's not exact. And even there, I'm working with degrees, whereas with this problem, it looks like we should be thinking in terms of radians instead. So I'm at a little bit of a loss here with this potential method, just because I'm going to need to add an infinite number of angles together, and it just won't end. So instead, I think we need to take like an algebraic approach with some trig identities too. The idea kind of starts with this tangent identity right here. This is just the tangent angle difference identity. Honestly, I don't know how to prove it myself, but I've seen it in a lot of like trig identity sheets, I guess, and I just trust it. And the idea here is that we're working with arctangent instead of tangent, so I need to like selectively apply some arctangents to cancel out the tangents, because they are inverse functions of each other. So if you take a function and apply it to the inverse, or vice versa, if you take the inverse and apply it to the function, you should just get the argument itself. So that's what I'm going to do first on both sides. I am going to take arctangent of both sides. And so that arctangent is going to cancel with just this tangent. And so we're left with alpha minus beta. I'm using Greek letters because it's like kind of standard to use Greek letters for angles, and angles are the input for like trig functions. And on the right side, I do just get arctangent of this whole fraction. But I want to introduce some kind of arctangent on here. Like my whole goal is that we have like some kind of like arctangent of something and then minus arctangent of something. And each term that we have is able to be broken up as a difference. Then the next term in the sum, I'm hoping, is going to be like arctangent of something minus arctangent of something. And the whole goal here is to get a telescoping series where all of these middle terms cancel out with each other. So it's kind of a lofty goal. Normally this doesn't happen if you just like have any random infinite series, but with ones that are like printed in math calendars, usually you're going to find some kind of fun cancellations with your infinite series. So additionally, what I'll do, alpha and beta are angles. Angles are also the output of arctangent functions. So I could just call alpha, say, like arctangent of A being now no longer an angle number, but like some kind of ratio of side lengths, I suppose. And we could subtract arctangent of B. And on the inside here, basically any time that actually here, first let me just get the arctangent there first and then open up these parentheses. Basically, I'm saying that alpha is equal to arctangent of this new A that I just invented. And if we apply the tangent function to both sides right here, tangent could just kind of attach to this alpha, and it's going to cancel with this arctangent. So anytime I see tangent of alpha in this formula here, I could just replace it with my new variable A. Likewise, this same thing works with beta or tangent of beta and B. And so I do get a slightly different looking formula here. Let's see, 1 plus and then A times B in the denominator there. Okay, so what this formula says is that if I have arctangent of a very specific fraction, I'm able to split the single arctangent into a difference of arctangents. And I'm hoping this is going to work so that we can cancel out a lot of terms. So we need to somehow make 1 over n squared plus n plus 1 look like an A minus B. So we need to apply algebra steps to this to get it to match that expression. And I think, let's see, let me move this 1 plus over to the left side and then factor out an n. So I have n times n plus 1. And so now my denominator matches. I just hope that I get the right A and B so that my A minus B is 1. Although, hold on, let me see. So currently it just looks like A is n and B is n plus 1. but that's no good actually, just because I want the 1 to remain here. So I guess it doesn't really matter. A or B could be either one right here. But let me just flip these around. So let's say this A is now my n plus 1, and this B is the n. So just to kind of match the formula from earlier, I could factor this out a little bit differently and do it as like n plus 1 times n. Multiplication is commutative. I can just flip them, no big deal. But then now when I do A minus B, I do get the 1 in my numerator that I had earlier. So now that I found this kind of very special setup for arctangent, let me get that arctan and then those parentheses around it, which this is exactly the same thing as this kind of summand term. I know that this is going to be the same as arctangent of, and then A comes first, which was my n plus 1, and I'll subtract arctangent of n. With this new expression at our disposal, now we just need to think of all the terms like n equals 0, n equals 1, all the way up to essentially n equals infinity, because that's like our top number. And hopefully we'll get some cancellations. I can kind of tell that we're gonna, because well, I'll just show. For example, when when n is 0, we have arctangent of 1, because that's 0 plus 1, minus arctangent of 0. And then we're going to have, for n equals 1, we'll have arctangent of 2 minus arctangent of 1. And here we have those arctangents of 1 canceling out. So this value is subtracted here. And so once we find the n equals 2 value, the arctangent of 2 will cancel with this one. And all the way down, we're basically going to be canceling out terms like this up until the very, very last one, where this previous term will cancel with that one, but we will be left with just this guy right here. This one doesn't have a pair to cancel out with, and so we will have this kind of last value in our infinite sum. Now it's a little bit strange because if it's infinite sum, why do we have a last one? But I could prove this with limits. I just kind of don't feel like doing it the right way. Here it's just all the terms will cancel, except we'll be left with this last one here and then kind of this first one here. And basically, once we plug in this infinity for n, the n plus 1 is still also going to be an infinity. So we have this kind of idea of plugging in infinity into the arctangent function. And we kind of need to think of this in a limit sort of way, because infinity isn't really a number, but more like kind of a concept here. So I guess fine. We will think about what is the limit as n goes to infinity of arctangent of n. And maybe the best way to think of this is to, well, actually, you could look on a graph. The arctangent graph kind of looks like this, where it passes through the origin and it has two horizontal asymptotes. This top one right here is the one that we're worried about, because as n approaches infinity, it's going that way. Essentially, this value gets so close to the asymptote that we essentially can call it equal to pi over 2. This kind of follows from the idea of where on, say, the normal tangent graph, we have vertical asymptotes at pi over 2 and negative pi over 2. This corresponds with kind of an angle of 90 degrees. So it's like trying to think about a right triangle that looks like this and doing opposite over adjacent. Once this reference angle right here hits 90, we no longer really have a triangle anymore, but just like a vertical line. And so this opposite side will be infinitely long, and this adjacent side will be infinitely short. And so it's kind of like we're doing opposite over adjacent. And in limit world, this is an infinity. So for our problem today, once we figure out this sum, or once we figure out that the sum kind of cancels out in a nice special way, and we're just left with arctangent of basically infinity, and then not forgetting about this arctangent of 0, minus arctangent of 0. But you could either consult a graph, I erased it, But how it like passed through the origin here, that tells me that arctangent of 0 is just 0. So we're only left with the pi over 2 value because subtracting 0 doesn't do anything. So that, I believe, is how you're supposed to get pi over 2 for the answer today. And this 2 right here corresponds with this x, and that is our answer for today. X is 2. Great. We're all done. Hope you enjoyed. I'll see you tomorrow. Bye.